I'm grateful for you guys inviting me to give this talk, and I just want to give you a brief description of what we do. So we basically, my job at JPL is usually on Mars, and it's on planetary exploration, especially robotic planetary exploration, and it's mostly been focused on Mars. Mars today, as we know, is very cold, and it's a desert. I've been working on Mars for the past 20 years. I work on all the rover and lander missions to Mars. And if we look at Mars a few billions of years ago, we could see evidence that there used to be a lot of water on Mars. And right now, we don't see a lot of water. So we're kind of curious as to what processes have led to this, right? And we also want to be able to know that whether Mars is habitable. So we've been able to, with the MSL missions and the Phoenix Mars lander, be able to establish that there used to be a lot of water on Mars in the past. We have ample evidence. And with curiosity, a decade ago, we've been able to establish that Mars can be a habitable environment. So our next mission to Mars is to look for evidence of extant life, or any evidence of fossils and things. On Earth, it's because Earth there's seismic events, there's very active. The evidence for very old rocks and other things are buried, so we don't see a lot of this. So if we're looking at things that are very old we can't find that on Earth, but Mars has been preserved for a long time. We might be able to find some of these giga-annum rocks. I show you, around Earth where we can see these types of rocks. So I'll skip this one. So when we go to Mars with Perseverance, what should we look for to be able to detect whether there's been microbial life or extant life on Mars? So these are the type of things we're looking for. We're looking for microbial biosignatures. So our payloads are been designed to be able to detect, when we combine this payload spectra, we should be able to tell whether there's any microbial signatures on there. And we know on Earth, we can travel to Shark Bay and we can see the modern stratomite around. These are microbial life that we see on Earth, and these are the type of things that we're looking for, rocks of this nature that we can be able to look at them and be able to glean into the past. And we also know from Australia, where we've done a lot of research, that if we go to the ancient rocks or Pilbara region, we're able to detect, we're able to see this microbial signature, right? So this is a nice picture of what we see, right? And then so these are the type of evidence that we'll be looking on Mars. If you can see things like that, we'll be able to draw that conclusion. So the question is, how are we going to go about doing that? And we do that by, the best way to do this is to find rocks that have this type of features and this type of signatures to return to Earth. So to do that, we are doing it in 3 stages. The first stage is Perseverance. We've set this rover on Mars a few months ago, and what it's going to do is we're going to roam around, we're going to do surveys, find rocks, and we're going to dig into the rocks, core the rocks, put them in test tubes, and then we're going to put them in depots on Mars, several depots on Mars. Then in 2026, 2028 timeframe, we work with the Europeans to launch an orbiter, and this orbiter would carry what we call a robotics capture system from NASA. And this orbiter will go around Mars and stay in Mars orbit. In the same year, we'll launch another mission, a lander, which is carrying a European rover that will land. This rover would go around and collect all the samples that Perseverance left in the depots and bring it to the lander. When it brings it to the lander will put it in a volleyball-sized container, and then it will do one of the first launch of a rocket from another planet and put the volleyball-sized container into Mars orbit. This can stay in Mars orbit for several years, even a decade. And then the European satellite that was already in orbit will rendezvous and capture the volleyball-sized container with all the samples. It will head towards Earth. It will release it into the Earth Earth capture region, and then it would, and the European spacecraft will fly away, and then this will land in the Utah desert in the United States, and then we'll pick it up, and then we'll send it to processing facilities, and then we'll distribute it among scientists around the world. So this is basically the architecture for sample return from Mars. This has been going on for over 20 or over 2 decades or 3 decades, and it's pretty exciting for the scientists to get a sample back to Earth so they can really analyze it. So that's our mission plan.
That's great.
So Perseverance, we want to understand the possibility for life on Mars. We want to look at ancient microbial life, human in preparation for human landing on Mars in the late 2030s. Okay, so we'll do geology, astrobiology, sampling, and then we'll prepare for human landing. And if you look at our past missions, we've worked on most of the surface missions that I see here, from our Mars exploration rovers to the Phoenix Scout to Curiosity to InSight. InSight was the last one that I did, and then the European one didn't launch last year. It postponed, and then we have Perseverance, and then we're planning the new mission. And these are the typical size of rovers that we started with Sojourner in 1997. We went to MER, and then we went to MSL. So we've been going bigger and bigger because we have much bigger payloads. So you can think of Curiosity and Perseverance as like Mini Coopers, if you're familiar with the British Mini Cooper. That's the size of those vehicles.
Okay.
See. So you get a sense of how big they are, and their wheelbases and their mass and clearance as well. So most people are kind of curious, where do we land? We land in this region of Mars called Jezero. And Jezero is a delta. When you go to deltas, you have a lot of water flowing in and flowing out, and they typically collect a lot of water as well. So on Earth, we know that in the deltas, that's where we find a lot of evidence of life. So if there's ever been life on Mars, it's most likely we might find rocks here that might have a microbial life. So that's why we chose this landing site. And then you can look at it, you can compare it to deltas on Earth. So this is how we think it was in the past. And if you look at the geology, it's abundantly clear. Okay, I'm going to skip the launch. I think you guys know about all this. We've landed, you know about the landing. And then you can, you've seen a lot of.
They said it was very.
So this is one of the first time we were able to actually put cameras to see our parachutes deployed, everything live. Be able to record it. We've never been able to see these things. We only see the telemetry that they work. So that was pretty exciting to see.
Indicate.
And this is the landing. I'll skip it. And on our past missions, we've been able to get our orbiters to take images of the deployed parachute. So this one was also very exciting for us to see that. We've seen it for our past missions. We have to time the orbiters and the landing very carefully to be able to capture it. And this is our first landing on first pictures from there. And then typically, we predict where our heat shield, all the things that we jettison are going to land. So we're able to predict them, and we're able to take the images, and we can confirm exactly where each of those things landed on Mars, and they're consistent with our models and predictions. And this is where, when they're students, we usually try to tell them how modeling is very important, and then how to verify your models as well. And it shows you. And then here you can see when our sky crane was jettisoned, and it kind of created a lot of plume, and that's basically dust. And here we have a sundial. When I'm on the continent, on the African continent, most people always think space exploration is foreign, and I always try to remind them that our forefathers that walked this land, prehistoric people, they walked the land and then they looked to the heavens. And what did they see in the heavens? They saw all these beautiful constellations and planets and all the fanciful stuff. And they admired them, but they did more than admire them. They actually mapped them. So they used stones and carvings to map them. And they just didn't map them for the sake of mapping them. They used it to make life better on Earth. And how did they use it to make life better on Earth? By creating calendars to know when to harvest, when to plant, when. So space exploration has been taking place on the continent of Africa for forever. And, we did it within the confines on Earth. and we're able to map the constellations. But today we have an opportunity to go outside of the confines of Earth to do exploration. So exploration is it's not foreign to the continent at all. So I try to remind folks of that. And it's the same thing NASA is doing today. Is what we're doing today is we look into the heavens to make life on Earth better.
Yeah.
And it's never changed since prehistoric times.
Yeah.
And it's very important for young students and especially people of minority to understand it's not foreign. It's something your ancestors have been doing for a long time. And when I see a sundial, that's what it reminds me of, because most of the people had sundials and they could tell what time of day it was. And we have a sundial here. We're very primitive and we do the same thing people have done long ago. And it is always a good into time so people get the confidence that it's not something out of their realm. It's something your people of the Stone Age were doing, and people of the computer age should be able to do better. And these are some of the rocks and other things that we found. And I'm going to talk about the surface mission, and that's where usually I typically work on the robotic arms and doing the science. So here you can look at the two rovers, MSL or Curiosity, and they look very similar, but they're very different. And we have several different instruments. We have 23 cameras on this rover. We have the MOXIE. MOXIE is pretty exciting because it takes in CO2. Mars is just full of CO2, and it converts it to oxygen. And this is very critical for human exploration of Mars, and it's built from MIT. We'll be able to convert a lot. First time we want to take a lot of CO2 and got oxygen out of it. So it's pretty exciting that the future of exploration of Mars for humans is very prominent. We have the RIMFAX, we have the SuperCam, we have the Sherlock, and we can basically do a lot of elementary chemistry. On this one, we're not doing wet chemistry. On previous mission, we've done wet chemistry, but here we're doing elementary chemistry. And then we're doing also mineralogy as well. So we can put these things on rocks and everything, and tell all the minerals that are in there. We can tell you the elementary composition of the soil, everything. And I think I also emphasize on the continent is also that, it's always an international mission. On Curiosity, we have a Russian payload. Here we have a French, a Spanish, and then a Norway payload. It's always been an international collaboration. And I was speaking to folks in South Africa 2 weeks ago.
Yes.
And we're interested in what kind of payload can African countries contribute. And I think the simplest payload is a camera. It's fairly passive. And those are kind of things that, small nations can be working on to contribute to space programs. And there's always an opportunity for people to contribute.
Okay. Yes.
I'll just show you some of the mass cam. This is the French camera. And then look at some of the SuperCam images that we got. They're very fine. And then we can also apply the lasers. One of the challenges of space exploration is you take an instrument that fills the whole room, and you have to tell the scientists to shrink it into a shoebox. Because we can only fly a shoebox, we cannot fly the whole thing. So the challenge is working with scientists to take something that's fairly complicated and then package it into a small shoebox. And so I always have a shoebox in my office. When the scientists come to me, I give it to them, say, you gotta get an instrument to fit in there for us to fly. So these are some of the images that you can see when we landed. And this is the arm, the first time we installed the arm. From us, you can see the drill in the middle there, and it was pretty exciting. Then we have some X-ray lithochemistry, that's Pixel. Hospital JPL, that is on the end of the robotic arm. And then we have a very high resolution, color camera for microscopic imaging, several microns. And this is the first time we turned the wheels on Mars. And this is the first time we drove recently. And kind of see it.
Look at that.
Yeah.
And then we have a radar imager on the system, the RIMFAX, that we can do ground penetrating radar to look underneath the surface that we're driving. And we can be able to kind of understand the mineralogy and the different layers of Mars. And then we have the meter, the Spanish, so we can measure the wind. On my previous mission InSight, it was one of the most comprehensive weather stations on Mars. And today, we still provide you daily weather forecast from Mars because we have pressure sensors. Here, they don't have a pressure sensor. They have a wind, and then they have a few other things. But we can literally give you the weather in the region of Mars that we landed very clearly. And this is the MOXIE that I was talking about, taking CO2 and converting it to oxygen.
Ooh.
And then we have ingenuity. So this is a technology that we worked on.
One.
So I can work on the rotor for this one, and
Uh-huh.
it's very exciting to be able to have a flight.
Okay.
I mean, how much did you put in this particular ingenuity thing? I mean, personally, what exactly did you do?
So this is a technology demonstration. This is the first time we've flown on another planet.
Yeah.
Right. So on Mars is a lot more challenging because the atmosphere is very thin. So you have a dynamic pressure issue. So you can see the first. This is the fifth flight where we actually listen. Can you hear the humming sound of the helicopter?
Yeah.
I can't. I
hear it. I hear it.
Oh, maybe I need to put the earpiece on.
Yeah.
Okay.
Yeah, so you can see that. So it's kind of pretty exciting to be able to take a technology to see how it works. So this is what we call a tech demonstration. It's a very it's supposed to fly for only 90 seconds. And if it does that, we're getting updated to understand flight on another planet. So this is going to be pretty exciting for us.
Very, very exciting.
But it doesn't do any science. It just takes images and it's just trying to understand how the technology works.
I see.
Well, it's good because it can go further than the rover. Or
depending on a whole lot of so if we look at the place that we've landed, this is the kind of features that we're seeing, and we can see clearly this was a delta in the past.
Yeah.
Okay. And on the robotic arm, this is what we do. We have a lot of instruments on the arm, and this is where we do all the science. We drill. We have different drill bits. We can change bits. We can have a dash, and I'll show you a few of the things that we do. Then we acquire the samples, we store them in test tubes, and then we seal them. We'll make sure that they're good to go. So this kind of gives you an idea. We have a tube. We can abrade surfaces with it. We can change the bits, like you change your drill bit at home.
Okay.
And then we can collect the samples, right, and put it in. And then we can seal the samples. We can extract the tubes. We can do some, and then we can seal it. So we do a hermetic seal of the tube so that when they come to Earth, we have the atmosphere of Mars captured in them so the scientists can get the whole picture. Then we can store the tubes, and then, we can do contact science as well. So this is what we will start doing in the next few weeks on Mars as the scientists select targets for us to collect samples from.
Good.
Wow.
And then we deposit in there. So this is the drill, and these are the drill bits. You see, they are all different drill bits, and then we can change them. It's a very complicated robotics operation.
Yeah.
And inside the rover, so we have a robotic arm outside the rover, and then we have a robotic arm inside the rover. So once the rover picks up the samples and it kind of seals, it gives it to this rover, the robotic arm inside the shard, and it prepares the sample, it documents them, and then it seals them for storage. And this is what it looks from the inside. It's a fairly compact and wonderful system.
Okay.
And typically when we have students, I try to show them, the diversity of the people that work here. I don't know whether this is going to work today, but it basically shows you what the opportunities that we have. Oh, it's not going to work today. I don't know. Your connection is unstable, it tells me. Okay. So this will show you people actually working.
Wow.
So once we've collected the samples, let me try again.
Okay.
I'll come back to it. I might be able to. So let's go. So once we collect the samples, we seal them, we actually drop them on the surface in a depot. A depot is an area that we drop them for the next mission that I described to come and pick them up. So when we land the lander, probably in the late 20s, probably 2028, 2030, it will have a European rover. The European rover would drive around, pick up all the tubes, bring it back to the lander. Then we put it in the volleyball container, put in a rocket that is inside the lander, and we fire it up into the Mars orbit. This is the first time a rocket will be fired from the planet. we kind of put in orbit. The European spacecraft with a NASA robotic system comes around, rendezvous with it, and captures it, and then returns it to the Utah desert. And then, so we try to ask the question: is life unique to Earth? And this is where the analysis will be done to answer that question. So JPR, we always say we dare mighty things.
Yeah.
So let me see if I can get the video to work. But I think that is all I had for you guys today. And
let's see. Anyway, okay. That's good.
I don't think I can get the video to work. Can you guys still hear me?
Yeah, well, we hear you. Yeah.
I don't think the video is going to work today for some
It's
reason.
Not, okay. Maybe.
Okay, so if you have any questions, we can talk. Oh, that's going to work now.
Oh, okay.
Can you see it now?
Yeah.
In terms of robots that go into space, the sampling and caching system on the Mars 2020 mission is the most complicated, most sophisticated thing that we know how to build. This is a system that allows us to take core samples of rocky material on the surface of Mars, carefully seal them in very sterile, clean vessels for eventual return to Earth. We've been working on this sampling and caching system for 7 years, and that's because it's a tough job.
We're testing the equipment to make sure that it's going to work when we get to Mars. It has to function on its own. We have to think of all eventual possibilities and try them here first. And then if they don't work, change it now, because we can't make any changes later.
To drill into the rock on Mars, pull out intact core samples, seal them hermetically, and to be all done autonomously by a robot hanging off the end of a rover on the surface of Mars has been a challenge. We've got actually 3 robots necessary to do the sample and caching system. Our big robotic arm out on the front of the rover, that takes our drill, pushes it against the surface, and allows us to take core samples. Then we put that core sample in the bit carousel, the second robot that takes that from the robot arm and puts it down inside our adaptive caching system. This is the part of the sample and caching system inside the rover. We've got a little tiny robot, a special robot arm called the SHAW, the sample handling arm. It takes the samples out of the bit carousel and moves them through volume assessment, image taking, and eventually to sealing, and then replaces the cylinder containing the sample in a storage spot, all on its own in the matter of a few hours. We have designs on bringing them back in a decade. Mars has been at the fore of our consciousness about the questions of life. Could life exist in one of our nearest neighbors? I think we have a lot to learn, life or no life, about the evolution of our solar system, about our planet, by looking in depth at rocks brought back from Mars.
Okay, so that's all I have. So if you have any questions, we can talk.
I realize the wheels, they are made from aluminum, right?
Affirmative.
Okay. And in case you have a bad wheel on Mars, what do you do?
Yeah.
So I don't know what you mean by have it bad. So we have wheels, you know, on MER. When I used to drive those Rovers, we had wheels got stacked. So we have, that's why we have 6 wheels. We're able to drag it and drive for years.
Okay.
On Curiosity, we have wheels with a lot of puncture in them because the rocks were a lot sharper than we thought, but we're still driving them. So you know, the wheels are put through what we call the life test.
Okay.
We create an environment, the Martian pressure and temperature, and we run it for what we call a life test 3 times, as long as we think, 3 times more than we think we're going to use it. So we build in margins as well.
Okay. So so there's no need to replace a wheel. Okay.
The way we do it, if you go to reactions, you can raise your hand. So I raised my hand. I mean, I did that way to ask a question.
Okay.
The weather conditions on Mars must be pretty hostile. So that means that these rovers and the ingenuity has to be engineered to withstand these very low temperatures. I think it's like minus 32 degrees Celsius for the temperature, if I remember correctly. That means that's a lot of specialization in material science. Do you agree with me?
So, we have the thermal, extreme thermal kind of excursions, you can go as low as minus 128. But so we distinguish what we call operational temperature to non-operational temperature. So these things are qualified to, if they're in their not operational temperature, they should be able to withstand up to 128. If you want to operate them, we typically are operating them at a minus 55, right? So we have heaters that if something cannot survive to minus 28 or something, what you're going to do there is you're going to provide it a survival heater that would keep it to that temperature. But you want very few of those things in your spacecraft because that's energy. It's going to use all your energy. So typically we have components that can survive to minus 28 without being operated. Then if you want to operate them, you have to bring them to the operational temperature. Either you wait for the environment to get you there, or you use your own heaters to bring it up to operational temperature. But the space arena does generate a lot of cold electronics and other thermal materials that can withstand the extremes. And that's what has helped a lot in the packaging of all this advanced electronics, consumer electronics that people see today.
Thank you. Thank you
very much. Yeah.
I have a couple of questions for you. How are you doing? Thank you. First of all, thank you for your presentation.
Thanks for having me.
Yes. So I was curious in looking at two things. One is you were talking about the oxygen conversion to oxygen. Have they actually calculated how much oxygen is able to be produced and the purity of that oxygen, so that if they need to use the oxygen for starting a fire or something? Have they ever started a fire on Mars to be able to see if fire is sustainable?
So I don't think anybody has. So so far the oxygen that they've generated, they've been able to tell the purity of it. You can just Google MOXIE and you see the experiments that they've done, and these are human grade oxygen.
Okay. And my second question was, you talked about the ancient African traditions within space and utilizing that. So I'm curious as to your thoughts on, for instance, the whole science behind Sirius B, right? So that if we look at, I think that's one of the most poignant kinds of ways to think about African understanding of the solar system, in that something that you technically can't see with the naked eye in the way that maybe we might think. But here you have a group of folks, the Dogon in particular, who were able to look at, understand, and utilize it. And it was believed for many years that they didn't know what they were talking about until Europeans were able to create telescopes to actually be able to see what they had already known about.
Yeah, so I think it's one. So I think we always have to bear in mind that the cosmos changes quite a bit. So when those ancestors were alive, maybe those things were more accessible in the visible spectrum, right? So when we came along and maybe the Europeans came around, it wasn't visible with that. It wasn't within the visible spectrum. So I don't think, so they could have, so I think it's fair. If you cannot confirm something, there's no observation, you can deny it. But once people were able to make that observation, I think they corrected it, right? So there were things that our forefathers could see that we cannot see today, right? And I just think we need to acknowledge that. And I think even most people are beginning to acknowledge that today, that there are things that if you live 1,000 years ago, the sky would have been very different at night. would have been very exciting, and I'm sure it was a lot clearer too.
Yeah. Yeah, blue and blue.
Any light that was
Nice
causing
blue.
reflection and
Yeah.
problems.
We have too many
absolutely right
satellites
on
these
that
days,
one.
so it looks very different.
Yeah.
That was Professor Khalfani of the Africana Institute, Essex County College. He's the director over there.
Oh yeah, nice to meet you.
Nice to be here. Nice to meet you too.
Yeah.
Oh, that's
so
yes.
from all the samples that you guys have been able to collect and analyze, is there any evidence pointing to the existence of life on Mars so far?
So I don't think so. We haven't collected any samples on this mission yet. We're in the preparation to identify the rocks that we need to collect the samples. So so you want to understand the processes that. So we say, okay, is there water on Mars? Has there been water on Mars before? We send the MERs. We were able to document evidence that there should have been a lot of water in the past of Mars because of our evidence that we see. Then we send Curiosity. We say, okay, is Mars habitable? Because we know on Earth, anywhere we found traces of water, no matter how acidic or anything it is, there's been life. So we went there, and then we started looking with that to see if there's some kind of wet chemistry as well to understand, is Mars, is it habitable? And the answer is yes. We have evidence to show that it's habitable. I work on Phoenix as well, where we dug the soil. We look at the soil, the alkalinity of the soil was very similar to the garden soil that you buy from Home Depot or anything. So nothing should prevent things from growing. So we know that it's habitable. We know there's water. And now we're going to look for specific rocks, like I showed you on Earth, to be able to see and bring those rocks back. And then looking at that to see whether there is any microbial life life existence. So that's the goal. So when people say, have you detected life? I don't think anybody is expecting to, be surprised to detect life, but maybe you can detect that life could have been present, right?
Is it possible that during travel and a landing on Mars that the equipment that is there could inadvertently bring bacteria or fungi or other kind of living substances, organic things that could adjust to the living conditions there and could then, I don't want to say contaminate, but maybe that's how you all would think about it, but that could then take hold and live there based on its transportation from place A to place B, and then be a foreign substance that then finds a threshold for which it can live and thrive.
Yeah, so we have what we call planetary protection. So when we're building the spacecraft on Earth, we actually bake the whole spacecraft to incredible temperatures to kind of kill out all the microbes that we know. And we sample the spacecraft and we measure, we do a lot of measurements and we go out of our way because we don't want to go detect our own life, right? So the question people have been asking is, as we're doing more research, we find that they're fairly hardened microbes that can survive some really extreme temperatures, both on the low end and the high end as well. So people are always curious, have we taken some microbes to Mars? But I can assure you, if you work in the clean room for a while, which I've done for several years, the amount of cleanliness and the extent we go to clean the spacecraft, and if you look at the kind of harsh environment that the spacecraft travels in terms of radiation and the entry, it must be a very hardened microbe. So that is what we call, forward planetary protection. Then we have backward. So now we're trying to bring a sample back. So that is another question for us. What is the protections that you have that you're not going to bring something back to Earth? And that's a much bigger question. And the way we seal the samples to make sure nothing leaks and we test it and everything, that is something that would come up very soon when the samples are going to be returned. It will be a big global discussion.
Mm-hmm.
Okay, so between the curiosity and the perseverance, I think the major difference is the internal and the external robotic systems, right?
It's more than that. The payload is completely different. So the missions are different in the sense that one was trying to get samples to establish habitability of Mars, and this is actually trying to identify rocks that we can bring back to Earth that would help us to determine that whether Mars, there's ever been life on Mars, especially in the region that we are. So that's the big difference between the two. Your institute, is it in Dallas or is it Houston?
No, this is in Newark, New Jersey.
It's Newark, yeah.
Oh, so it's part of Essex College, okay.
Yes.
Okay.
Yeah, in fact, this is our 20th anniversary. So we're looking to, this year, we're going to spend the entire year celebrating 20 years of Africana Institute at the college.
Okay, it's pretty cool.
20 years already, thank Christ.
Very fortunate.
Okay.
Okay, so if there are no more questions, like I said, I have an impromptu meeting that I have to go at 4. I want to prepare for it, but it's an honor to talk to you guys and to engage.
Okay, so we stay in touch because I mean, for sure, we hope one day we'll get a chance to come and visit you.
Same here.
Yeah.
Okay.
JPL.
Oh, where are you located? I thought you were out here.
No, I'm in Pasadena, California.
Pasadena.
Oh, okay. So you're at the
Jet Propulsion Lab.
Okay, Jet Propulsion Lab.
Yeah.
Okay. Good. Yeah, I have someone out there I know. Robert. What's his last name? Maybe he works on the computing side, so he might not work on the same side as you. Can't remember his last name. Anyway, another African American who works at JPL.
Okay.
So I'm glad to see there's a diversity of folks that were working on the projects. That's always important, because in fact, when I finished my doctorate back in 2004, I was working on a project called Race in Space and the Space Race, which looked at, I'm a sociologist, so it looked at the fact that, dealing with the whole space, the race in space and to space, that there was very few non-Europeans involved, or, well, no, I guess it was Chinese and Japanese involved, but there were no Africans involved for the most part. And I guess still today, according to your point, is very few or maybe no African countries who are currently have anything in either in the space station or in any other kind of capacity. I don't know. Is that accurate?
So I think there's more to space than most people kind of look. So if you look at South Africa is the world leader in radio astronomy.
Mm-hmm.
Because what the South Africans have done is just sheer genius. Their geographical location is amenable to that type of exploration. So instead of them saying, hey, we're going to do everything everybody does, they just look at a geographical location and they invested a lot of money. So they have a lot of arrays. NASA has to build their own. Anybody that wants to do radio astronomy, they have to go to South Africa.
Oh.
And that's one of the things that when I talk to the AU, African Union, and other African countries, it's not about sending up somebody to walk on the moon. It's by looking at your geographical location and looking at your economic thing, and then you select something that works for you. But what works for the United States and works for Russia and China might not be the thing that might work for you. And South Africa has done they've done a great job, and they get a lot of money put in because nobody wants to start the infrastructure again. They just go there and just do their job.
Okay. So I remember my bigger question that I wanted to ask. And I know you got to run, so I'll make it quick. I just was curious. I've been curious about this for a long time, and that is, we have this push for looking for life in space, but we use the markers of life as we know it. But what if life in another place didn't need the things that we need? So, for instance, that if running through their veins was acid and not blood, whether they didn't need oxygen, that they needed, some other substance to sustain life, completely opposite to anything we've ever thought about? And are there ways in which you all are looking for life other than things that would need water or this or that, and there could be a completely diametrically opposed maybe way of thinking about life as it is?
Yeah, so you're talking about carbon-based life. So the instruments that have been developed to detect this microbial life is able to distinguish, although we don't know the different lives, we'll be able to see the signatures of them because it's basically elementary compositions, right? So you might be able to dictate, oh, there's a structure there. So it's just looking at structure rather than looking at, we don't expect to find any living organism, but we want to be able to find the signatures of potential of past or extant life. Does that help? Just like we see fossils in rocks here. Yeah.
Right.
At the microbial level. Okay, so I really appreciate you guys having me, and I need to run. So
thank you for coming. Thank you for coming. And by the way, thank you for your work on the Ghana Robotic Academy.
Oh, my pleasure. Yeah,
thank you for helping the young kids, at least they have some future in robotics. I don't.
Okay, Obeshida. Thank you.
Santi.
The saying is, we are very, of course, honored and just it's so beautiful that you've reached that level, coming from Ghana, making Ghana proud, making Africa proud, because I know it's not a joke. This is high-level technology. So what's your advice on Ghana and Africa also kind of getting up in technology? What would you say to that?
Started.
So I don't know what you mean by getting up in technology. So I think currently we are good consumers of technology, and it's just a good thing. What we try to do with the Ghana Robotics Academy Foundation is to make kids not just be consumers of technology, but to be people that have the confidence to know they can generate technology to solve their local problems. And the way we've done, we've done that is we've been able to bring them to international competitions, and they've been able to do well and build confidence. So we have a lot of students. Actually, we had a student graduate from Berkeley recently. We went through the program, and we have a few people at University of Pennsylvania. So what happens is when you take the kids to international competition, the first time we took, because we use the same software, every nation uses the same software, it's a level playing field.
Yeah.
And I remember one of the kids coming over to me, I don't know where we were in Malaysia or somewhere, he comes and said, look, the German students came and asked us to help them. And it blew the kid's mind. He said, these people are from Germany. So, and that's the problem. People feel that when they see things on TV, these people are way advanced than they are. So when you take them to these competitions, what it does is that it boosts their confidence that, wow, we have the same skills. If we have the same tools, we can do exactly the same. And we've been the kids that we've taken to competitions, and they've worked internationally, their confidence, they do so well in school. Any kid that takes our program, they do well in school, because basically you are encouraging that. And the other thing that I'm really passionate about is connecting science to practice. So every competition we do, they use the things they've studied in school on the robot. Because I think my experience with science in Ghana was more theoretical. They didn't make it. The teachers couldn't show you how you're going to use it in the real world. So doing that connection actually helped even people that are doing business to switch to science, because they realized that no, science is not as bad as we thought, because they've been told you cannot do science because you cannot memorize the stuff, right? But now that they could actually, it just it's a diamond. I don't want to go into brain theory here, but once you expose people to certain things, the neurons connect, and they become geniuses. People, medical school, they've changed. So I think that's, to me, is the exciting part. It's not the numbers. It's just giving people the confidence and people connecting that you can actually, whatever you're teaching in the classroom, is applicable to solving your everyday life problems.
Yeah.
And to me,
That's
that is what
right.
was going to change the continent. It's not.
That's right.
Yeah.
Wow.
That's right. Yeah. Thank you
That's
very much
right.
for. Thank you for your insight. I mean, it's no small feat what you've done in Ghana. Robotic Academy.
Thank you ever so much, and let's keep in touch. And I really appreciate your time. Okay.
Yes, thank you.
Thank you. Bye bye.
Okay.